Hi, my name is Jim, and today's topic is distortion and cross products, which we encounter a lot when we're dealing with communication signals, including audio. And we're going to start our discussion here with a linear amplifier, and they really don't exist in the real world. All amplifiers add something bad to a signal, noise, distortion products, and the like, but we're going to ignore the little bit of artifacts for our discussion here. So I'm going to be sending a sine wave in, that we can see this here in the time domain, and if we were to look at that with a scope with a best Fourier transform function, an FFT, or a spectrum analyzer, what we would see would be a spectral spike in the frequency domain. Now, Fourier was a mathematician that lived many years ago who figured this process out, and it's so very useful to us in electronics today. So in both cases, what we can see is the amplitude of the signal, and in the time domain here, if we get a complicated signal, it's very difficult to see different frequencies, and in the frequency domain, it's just about impossible to measure phase differences. So each domain has its positives and negatives. So we pass this through our linear amplifier, and as we expect, the output is going to be the gain times the input. So in the time domain, we see a larger amplitude sine wave, and in the frequency domain, what we see is a spectral spike at 1K, which is also larger. Now let's move on to a linear amplifier, only this time we're going to put in two frequencies, and the ones I chose are 350 and 440 Hertz, which comprise dial tone. These are sinusoids mixed 1-to-1, which means the amplitudes are the same, and I'm showing the 350 as having a longer period than the 440, and if we look at this in the frequency domain, we see spectral spikes at 350 and 440 Hertz. So it goes through our linear amplifier, and if we take a look at the output, well, it can look kind of strange. And it's hard to tell in the time domain what frequencies are in a signal. As a matter of fact, we may not even know if it is a linear amplifier. But in the frequency domain, here's what we have. 350 and 440 Hertz coming out, and the spectral spikes are larger because of the gain of the amplifier. So, all is well. Now let's move on to a system which isn't so linear. And suppose that we have a little device like this guy, and this is designed to run from a lithium-ion battery, and these little guys here are operational amplifiers. Here we go. And a fully charged Li-ion battery is 4.2 volts, and its cutoff voltage is 2.8 volts. And suppose that we're listening to music through this, which is one of the functions of it, and we're pushing it kind of hard, and we're near the end of life on battery, so the operational amplifier that's driving the headphones is running into the supply rail. So that would be like 2.8 volts. So these op amps that I speak to in here are called rail-to-rail. They're CMOS, and they're a later technology, and they're also more expensive. But if we hit a supply rail, well, we can't go any higher, really. If we call this here 2.8 volts, and this down here would be 0 volts, should have centered that better, is we're going to get a clip. Now, what that clip does is it converts the sine wave from something that's pure into something that isn't. So in the time domain, we'd be putting in a pure sine wave, and we can kind of see that in the frequency domain here. And then coming out of it, we have a clip, and if we look at that in the frequency domain, is what we see is not only do we have the 1 kilohertz signal that we're putting in originally, but we also have a whole number of multiples of it called harmonics at 2K, 3K, and so on and so forth. So let's take a listen to what a good sine wave and a distorted sine wave sound like. Now this is the good sine wave, and this is the sine wave with distortion. good, distorted. Now the reason it sounds different is because we have additional frequency components in it. May or may not be a bad thing. So let us continue here, and this would be a nonlinear amplifier with one input, and now we're going to put in two inputs here, input A and input B, into a nonlinear amplifier. And if we look at the frequency domain, we see that our input tone sources, frequency sources, are pure. It's two spectral spikes. That's a good thing. And what we have coming out in the time domain again is, well, not so easy to see. And in the frequency domain is we end up with kind of a mess. Not only do we have the original frequency components A and B, is we have their sums, A plus B, their differences, A minus B, plus the sums and differences of all the harmonics associated with A plus B, plus the sums and differences of the harmonics and the fundamentals, plus. So what we get out here is a spectral mess. And that is called the cross products. And also we have some signal components, and we have harmonics. Now, typical name for this is intermodulation distortion. And if it's not desired, it is called distortion, and distortion means what it means. It's distorted. It's not the way it should be. Now, if we were listening to music and we were running 2% IMD over a period of time, people would become kind of fatigued with it. It would kind of grate on them a little bit. However, if you're in a heavy metal band, guitars are highly distorted, and that's to give the fuzz sound of it. So that would be a place where it's desired. Further, it can also be desired, and under the circumstances it would be called modulation. And without cross products, we don't have any radio or TV. Modulation is the process of taking information and putting it on a higher frequency signal called a carrier. For example, voice signals on 1.1 megahertz WTAM. It's a modulation process, and it's very, very nonlinear to make that happen. So like everything else, it has its place. Sometimes it's desired, and sometimes not desired at all. Next thing is, how does the industry measure distortion? And the answer is that they have designed this equation as such. Harmonic distortion equals the square root of the sum of the squares for all of the harmonic voltages divided by the fundamental, and to express that as a percent, it's times 100%, and it could also be expressed in decibels. So suppose I have an amplifier here, and my fundamental or first harmonic, now this is the guy that we want, is 10 volts, and it's kind of nonlinear. We have some distortion present. Second harmonic is 2 volts, third harmonic is 1 volt, and the fourth harmonic is 1.5 volts. Now there's no rule that says that these have to be decreasing. They can increase, and do, and as a matter of fact, depending upon what the signal is, what the amplifier distortion is, things like that. So to find out what the HD is of an amplifier which would have that output signature, if we just plug in the values and work the math, as we see that comes out to be 26.93%, which is terrible. Would not want to listen to any public address system with that kind of distortion. Next, how do we measure this on a scope with an FFT function? And that's a math function, or a spectrum analyzer. Well, a little more difficult here is we just don't have these nice presentations with a linear arrangement for the amplitude. Instead, what our scopes do is they provide an output in decibels. And each mark here is 10 dB. Now, you might think that that's kind of an unnecessary thing to do, but the dynamic range of what it can display is enormous. Plus, you can scale this down where each centimeter could be, say, 5 dB or 2 dB to make a very granular measurement. So typically what sits down here is the noise floor. Kind of looks like this, actually. And suppose that our fundamental in this case is 1 kilohertz, and we measure this at 10 dBV. And our second harmonic is negative 20 dBV, and our third harmonic is negative 30 dBV. And we want to find out what the harmonic distortion is of whatever equipment we're measuring. Well, as you can probably guess, we have to convert from the log domain into the linear domain. And one of the things that you absolutely have to be sure of when you do this is what is the reference of the device you're using. Now, the scopes that we are using have a reference of 1 volt RMS. Some of our simulation software is 1 volt peak. Video signals, 1 volt peak to peak. DBU, 0.775 volts RMS. So there's many different references. dBm, 1 milliwatt. So you have to be familiar with the equipment you're using to accurately measure this. But fortunately, converting this from the log domain into the linear domain is relatively simple. So let's take our first guy here, and the general equation is dBV equals 20 times the log of V1, that's this guy, divided by our reference, which is 1 volt RMS. So we solve this the way we'd solve any decimal problem. We'll clear out the constant that's multiplying the log operator. Dividing both sides by 20 gives us 0.5, and then we take the inverse log of both sides, which would be 10 raised to the 0.5 power equals our voltage times 1 volt RMS. Now the easy part is all we do is multiply this guy by 1 volt RMS, and what we see is we get a voltage of V1 of 3.16 volts RMS. So that would be this voltage here if we were to measure it in the linear domain. But we've got it. Let's go on to figure out what V2 is, and that's minus negative 20 dBV. Sets up the same way. Doing the math is 10 to the negative 1 equals V2 over our reference, 1 volt RMS. And solving for V2 then gives us 100 millivolts RMS. Likewise, V3 gives us 31.6 millivolts RMS. So then, if we take and insert that into our harmonic distortion equation, is what we see coming out of this is 3.32%. So that would be considered high for a stereo amplifier today. Again, in the numerator, it's the square root of the sum of the squares, and what that does actually, it gives us the effective voltage in the numerator. That would be the voltage which would produce the same amount of heat in a given resistor as a DC source, and that is the way you do it, the square root of the sum of the squares. So, in this case, our distortion is a whole lot better than what we've seen before, but really not acceptable for high-fidelity work. Now, when we're going to be dealing with cross products, this has to do with figuring out all of the different frequencies that result from more than one signal entering a nonlinear device. And it doesn't have to be an amplifier. It could be a device called a mixer, whose purpose is to generate cross products. They're in every radio, in every television, cell phones, everywhere. So for our example here, let's pick two frequencies. I chose 2 kilohertz and 6 kilohertz sine waves, and we're going to send these into a nonlinear amp, and the question becomes, what are the output frequencies of the amplifier? Now, we're not going to be interested in voltage because that would be a very, very difficult calculation if possible. So first off, if we want to answer this, is we got to start with the regular harmonics because they're part of it. So the 2K, since it's going through a nonlinear amplifier, will have a 4K and a 6 kilohertz plus 8 kilohertz whatever component. One of these could be 0, don't know. And for our 6 kilohertz input signal, since it's being distorted also, as we have its second harmonic and third harmonic and so forth. And then in addition to that, we get the cross products. So we set up this chart, and we have these two variables, M and N, and they don't stand for anything other than M and N. There's nothing special about them. And I've let M equal 2 kilohertz and N equal 6 kilohertz. And what this is going to do is produce or tell us what the sums and differences are for these two frequencies. So to start with here, let's take a look at 2K plus or minus 6K. That's 1 is 1 times 2K, and N is 1 times 6K. So these are the base frequencies. So if we plus and minus these guys, add them and subtract them, we see we have frequency components produced at 4K and 8K. Now we're going to take 2K and mix it with 2 times 6K. So that would be 2K plus or minus 6K times 2, which is 12K. So 2 plus or minus 12K gives 10K and 14K. And notice that we don't get into negative numbers. It's just the frequency is going to be the difference. Next, we're going to take 2 times 2K and mix it with 1 times 6K. So 2 times 2K is 4K, plus or minus 6K gives us 2K plus 10K. Finally, we have 2 and 2, so 2 times 2K is going to be 4K, and 2 times 6K is going to be 12K. Adding and subtracting those, we get components at 8K and 16K. Now, as you can probably guess, is we could have another column here called O and P and so forth, and mixed 1 with 3 and so on and so forth, but the most we're going to do is 1 and 2 for multiples of our fundamental frequency. So these would be the frequencies that occur in the cross products, and many times these are very, very necessary. For example, if you tune in a radio station, the antenna feeds a device called a mixer with a whole bunch of different frequencies. And another device called a local oscillator generates one sine wave that's higher than the frequency that we want to tune to. And these go into this very nonlinear device, and we get the sums and differences, and we take one of those differences, tune it, get rid of everything else, amplify the heck out of it, detect it, it's hard to put a diode in series with it, connect to an audio amplifier, and we have an AM radio. So it's the difference between the local amplifier and the desired station, which is being selected, tuned, and ultimately sent to our speaker. Without cross products, we don't have a radio. The diode detector that I mentioned basically is very nonlinear also, and that deals with cross products to get from, say, a frequency of 455 kilohertz down to audio baseband stuff we can hear, all based on cross products. So that's about it for cross products and distortion, and thank you for watching.